Welcome, everyone. Welcome to our webinar today. I'm Monica Stocka, and we're very pleased to present today. First, some housekeeping. Everyone should be on mute at this time. If you have any questions or comments, please enter them into the Q&A section. And at the end of the webinar, we will answer as many questions as time allows. We're also recording this webinar, and everyone in attendance today will receive a copy of the recording. We're going to break up the presentation a couple of times with poll questions, and those will appear on your screens and you can select your answer. So for those of you who are not yet familiar with TotalSim, we wanted to give you a little bit of background. When TotalSim first began in 2009, we entered the CFD market in the motorsport and automotive sectors. Our co-founders, Ray Lito and Nathan Eagles, both spent NASCAR and Formula One respectively in the 1990s and have continued to be on the cutting edge of technology since then. TotalSim now spans across 11 different industries with successful projects in everything from aerospace to even Olympic cycling. When working with our clients, TotalSim engages from wherever they might be on their simulation journey, and we help clients solve their problems with efficiency and accuracy. From clients who have never used simulation before or CFD to those who are looking on guidance on how to set up an in-house CFD department. We recently joined the Siemens family as well as a partner for STAR-CCM Plus. STAR has been our preferred CFD solution for many years, and we have used it in countless projects. Along with CFD consulting and being a software provider, we also offer a wide range of other simulation services, which you can see on your screens. Our speaker today, Greg Patchett, has been a vital member of the TotalSim team since 2011 and brings extensive expertise in top-level motorsports. Greg graduated from The Ohio State University with a bachelor's in mechanical and aeronautical engineering. He's our go-to expert for testing new tweaks to our CFD codes and methods, and his work with NASCAR and championship-winning GT and prototype series cars, sports cars, has been instrumental in developing our internal multi-car drafting capability. And these capabilities are actually used by every manufacturer in NASCAR and NASCAR R&D today. So this is actually the time for our very first poll question. And this is a little bit different. So you have to put in your answer in the Q&A, and we'll share the results at the end of the presentation. And the question is, who do you think is going to win which NASCAR driver do you think will win the championship this season? And I'm really curious to see who y'all pick. And now I'd like to hand this presentation over to Greg.
All right, thanks, Monica. I'll go ahead and get started on the discussion we have with what we did with NASCAR about a year and a half ago. So I want to give you a bit of background on what NASCAR was looking to do, what they'd done previously leading up to this. We'll get into some of the details of the case setup, some of the material properties going in, look a little deep at first, then we'll kind of back up and look at some of the initial results, looking at the exhaust they started with and the final exhaust they ended up with, along with some changes they tested and held on to for future use if they want to use them. And then at the end, we'll have that Q&A that Monica said. So NASCAR moved from their Gen 6 to what's now known as the next gen back in 2022. And when they did that, they went from a sort of open floor design style NASCAR model that had been used for, decades at this point. And they hit their stride with this new flat floor model and had a whole new design that came up with that whole new front end, underfloor, back end. And with any new radical car change like that, there's obviously always going to be challenges. And NASCAR has been meeting those challenges as they come and continually, making the car more robust and maintaining its racing capability while doing all this at the same time. One of the concerns that had popped up for just comfort purposes and controlling temperatures was cabin temperatures. And there's quite a few sources of heat now on this next gen model that hadn't previously been a concern. With an open floor previously on the Gen 6, uh, there was a bunch of air that would just flow into the car and carry a lot of heat away. But when you go to the higher performance flat floor models, now suddenly you have to route exhaust through rocker boxes and along the sides of the vehicles. And that leads to a lot of heat buildup, and it becomes a heat management challenge. Another consideration was the radiator ducts that had been moved to the hood, and those were pumping hot air, across the top of the car, across the A post, and some of it was getting pulled into the cabin. So ever since the car has come out, NASCAR has continuously been making this car more robust for heat management, and they've done things like add the window NACA to help cool the drivers, changing how the A post window has a design to flick away the hot air. Uh, they've gone through and made changes to the floor to help try and vent uh, all that hot temperature out away from that exhaust, openings in the floor to try and provide as much cooling capability as they can to help maintain those temp or mitigate those hot spots and hot temperatures. But it's obviously going to be a challenge, and they've done a lot of work. But one of the things they wanted to change with this was to move from a long exhaust to a short exhaust to try and get a lot of that heat rejection removed from the model or from the car. So all this work was done in STAR-CCM. At the time, it was version 2306. And I have a bunch of stats up on screen so you can see sort of the settings we were running at. This was done at a street course setup. So this was done at 60 miles an hour, one of our standard very large domains around the car. We were doing this steady state, but we were doing it with conduction, convection, radiation, all that present. And we were modeling a lot of solid components in this car. So it wasn't purely an airflow based model. We had all sorts of parts in here that were solid. And I'll get to those here in a second. But some of the other things that we had to model in here was what a proper heat soak on the engine bay and the car itself would look like. So we had to set up a bunch of different temperatures to, adequately capture that. So we have, an engine block that's setting at 300 degrees Fahrenheit, front rotors that are up over 1,000 degrees, calipers that are heat soaked up to over 300 degrees Fahrenheit, rear rotors sitting there at over 800 degrees. And then the big consideration in this was the exhaust itself. We did not set an actual exhaust temperature, but what we did with that instead was we set the exhaust flow going through the exhaust pipes coming in from the headers. So we set that 1,100 degree Fahrenheit flow, and then instead of saying that, oh, the exhaust is just simply 1,100 degrees or 800 degrees or some average temperature, we let the airflow inside there determine the convection and then the conduction through all the materials, and then how that convects and radiates out from the external surface of all those exhaust surfaces. As I was saying, with all the materials that we had to keep track of, it wasn't purely just the exhaust. And while that accounts for, the first 4 or 5 of these materials, such as Inconel and various versions of stainless steel and stainless steel insulating foil and insulation mats and radiation shielding and reflective films and all that. There's a lot of other parts in here, such as what the carbon fiber and the carbon fiber core materials were, so that we had an appropriate heat conduction and convection and radiation coming off those for any heat that's heat soaking into those. And all those have their own properties. All those have things to track along with those. And since we're doing radiation, we have to track all the reflectivity off those as well, and the transmissivity. Fortunately, we weren't doing any of the plexiglass or glass here to add another layer of complications. One option that was available that we did not do was solar radiation to, see how much hotter things would be, on a sunny day versus a cloudy day. But that is an option that could be done. We just didn't do it in this case. Uh, so before I continue on and get into how the model looked for the first set of runs and where we went after that, I'll go ahead and pass this back to Monica for our first poll.
Thank you, Greg. And we have our first poll question, which should be popping up on your screens right now. And that is, if you're doing simulations currently at your company, whether that be FEA, if that might be CFD, 1D modeling, either a 1D modeling tool or like Excel, or if you're not doing any of those things quite yet. And you'll have some time to add your answer. And if you haven't answered the first poll question about who you think is going to win the championship, you're more than welcome to add that as well. We're going to leave this up for just a little bit. A lot of CFD users among you, I see. Thank you very much, everyone. And now I'm going to hand it back. I'm going to hand it back to Greg.
All right. Thanks, Monica, and thanks everyone for answering those poll questions. We'll have another one coming up here in a little bit. But in the meantime, we'll get back to thermal management. So these first results right here are looking at the baseline model that we had run. And this was at, like I said, the 60 miles an hour, and there's a lot of interesting things kind of happening here. So these first two pictures are looking at the center line of the vehicle. First one's temperature, second one's velocity. Out of that radiator heat exchanger cores, we have 250 degree air coming out, which we saw on that first one of those first couple pages, the hot flow going across the hood. That's the source of that. Inside the engine bay, you can see all this hot air swirling off of the engine itself and building up a fairly hot engine bay temperature, which is not surprising given that you have a engine in there and exhaust pipes or headers potentially glowing. But also a critical factor in this is if we look at velocity, there's a very little airflow going through there, which is unsurprising given that you have sealed up front fascia, the radiator duct is completely sealed from inlet to exit through the hood, and one of the main exits is either through the wheel arches or going down this centerline prop shaft tunnel. Another thing to consider too is there's a differential cooler here in the back, and that's collecting air off the rear quarter windows and blowing that hot air down into the sort of rear trunk volume. And you can see that coming down, and since we have a little bit of air coming down that prop shaft, that sort of meets in the middle with where this hot air comes forward and some of the cool air comes back, and there's a bit of a mixing zone here in the middle of this, which when we get to some pictures in the cabin, you'll actually see some of this hot surface or warm surface on the cabin side. Now, if we look in an X cross section and we're looking a little bit in front of the firewall behind the rear wheel or front wheels, you can see the hot exhaust right here, and you can see just these plumes of hot air basically filling up the engine bay. There are two little circles right here that you can see. Those are exhaust cooling ducts that NASCAR designed and built into the next gen model so that it can pull cool air from the front of the car and direct it right back to the collectors on the exhaust. So once they basically get back into a plenum space, there should be a clear source of cool air blowing across the exhaust and helping vent all that heat out. If we look a little bit farther back, this is looking behind the front firewall, maybe 6 or 12 inches behind that firewall. And this is where one of the big challenges comes with trying to cool these exhausts. So even though NASCAR had put in a floor cutout, and that helped relieve some of the temperature buildup that was happening inside those rocker boxes, these closed volumes here, it's a hard fight to win when you have that, just because in a straight condition, you're basically fighting against these wheel wakes that are sitting here. So you have nice strong flow on the bottom and you have fairly strong flow a little bit away from the car, but it's difficult to try and cool the exhaust with that wheel wake present. So there were a couple things they wanted to address, and one of them was getting rid of that cutout, though it had helped on the long exhaust. They wanted to no longer have to rely on it and have something that was cooler and more robust in the end. This is a plot that came out of STAR. What we did was took the exhaust assembly for the headers all the way through the collectors and into the tailpipe, muffler, and exhaust exit, and pulled off a surface average temperature down that entire length exhaust. And up here where the headers basically start getting all that exhaust gas, while the inside of that pipe is seeing air that's 1100 degrees, once it's reached the exterior side, we're up at around 840 degrees. Roughly in this position right here is where that cooling flow from the nose blows onto the into the collectors. So you can see there is some cooling that's happening. And once these collectors come into a single pipe, a little bit more mixing, a little bit more turbulent flow right there. So we've got more heat transfer onto the pipe itself. So that's why you see that spike come back up. And then once we have, or this other dip right here is where on the side of the car we have some vents. And this is one of the places where the hot air can exit. So we saw a little bit more heat transfer there, cooling off the exhaust. But then we don't have a whole lot of cooling down the rest of it. There's some there and it's getting cooler. But this is one of the things that NASCAR is working to adjust. So NASCAR was able to take these cars to the track, get some track data, and they were able to take some FLIR images, so looking at the infrared surface temperatures on the vehicle. And this is for the same setup between what was run on track and what was done in the simulation. And all these surfaces that you see here were modeled as thick surfaces, so they had full heat conduction and convection from one side to the other. So in this case, for the cockpit, from the underside up through the floor, with all those material properties, being taken into account. So initially, when they had run up here along this frame rail, they were seeing peak temperatures up around 130 degrees. Back here to the side of the driver's seat, you can see sort of opaquely here. They were seeing about 120. Over here on the other side, about 122 as well. And up here, similar idea. So we don't have exactly the same matching temperatures. The CAD model versus anything that was on track and physically built, we're going to have slightly different models. This doesn't have all the welds in it. This has different air gaps in it for manufacturing tolerances and things like that. But we're seeing the same sort of trends. We're seeing the same sort of hot spots in the same locations. So to us in NASCAR, that was a good indication that we had a good firm handle on what the actual conduction paths were, and we were going to be able to help them address their heating concerns. And you can see this FLIR shot over on the other side too, where they have that exhaust temperature, and that's coming out at about 820 degrees. So that was in the realm of what we were seeing as well at the end of the exhaust. So before I continue on to how the short exhaust helped with helping all these cooling issues, I'll pass this back to Monica for our next poll question.
Thank you, Greg. Yes, time for more questions. And as a reminder, if you have questions more related to the presentation itself, feel free to put that in the Q&A anytime throughout this webinar. And the question today for the poll is, if you're currently doing simulation, for those of you doing simulations at your company right now, sorry, it's the wrong question. What are the common challenges you're encountering currently at your company? Is it kind of the topic of today, which is thermal management? Do you see fluid structure interaction or FSI? Are you seeing some multi-phase simulation? If there are other things that you see pretty commonly, feel free to put those in the chat as well. And we're just going to give everyone a little bit of time to enter their information. And then if we can share that information in a couple minutes, then that would be helpful, I think. Perfect. A lot of thermal management, which is we kind of expected. But thank you so much for participating. And then I'm going to give it back to Greg again.
All right. Thanks everyone for answering those questions. And now we get to the fun animations. So there we go. So this is showing some streamlines coming out of that cooling duct that was routed all the way back into a plenum area where basically all the exhaust is run. And what was happening due to this muffler being back here, it was partially blocking up some of the flow from this cooling flow, not being able to get past the muffler. And that was basically cooling off the front of the exhaust, but not adequately cooling off the back end of it, which is where some of those temperatures on the side of the cabin were coming from. And because there's a bit of a blockage there, some of the flow that comes in swirls around, picks up some of that collector and header temperature, and swirls it back into the engine bay, which is what you see with some of those hot spots back here on the firewall. So while the firewall is insulated for thermal radiation due to the collectors themselves, the NASCAR wanted to go through and help remove some of that additional convection heat transfer that was happening there. And fairly similar setup between left and right. There's a little bit of difference in the headers between the left side and right side of the engine. So we see actually on the right-hand side a little bit more heat transfer into the firewall than on the left-hand side. So I'll start off with the short exhaust, looking at its initial results on the same sort of streamlines, and then we'll kind of back up and look at some of its effects on the rest of the cabin around it. So when NASCAR went through and redesigned this slightly translucent surface through here is one of the crush panels on the side of the vehicle to help for driver safety and car, performance. And what they have here when they redesigned this is they've increased that volume all the way around this muffler and the tailpipe exit so that all the cooling flow that comes in here has adequate opportunity to go through and cool off all this exhaust and then actually exit out the vents without having to recirculate into the engine bay. And if I go ahead and play those animations, you can see the flow coming in, a little bit of recirculation around the exhaust, but then a lot of it blows right out those cooling channels as intended. There's a lot less going back into the engine bay, and you hardly see any sort of heat or high temperatures here on the firewall. So it's doing a really good job with this new redesign in opening up that space, letting the cooling ducts do their job, supplying cool air to those exhaust pipes, and in the end, helping provide cooler sidewalls. So one of the other changes that becomes really obvious when you look between the original exhaust and this new short exhaust is its effect on the side of the cabins. So if we have the exhaust present here and you can see basically all the radiation and convection effects on the side of the cabin, there's this long region of just hot surface from sitting next to the muffler. Actually, if I back up here, I want to point out another feature is this closeout panel. So this helps also all the airflow that goes in here exit out the side. So if I flip back here, that closeout panel is basically right here. Now that all that hot flow is blocked from going down in the rocker box next to the cabin, there's a massive reduction in temperature and heat transfer through that cabin surface. And with all that additional volume around the exhaust to help that cooling air circulate around there, you see much lower temperatures across the firewall as well now that the cooling flows much more effectively venting out, and there's less recirculation. So that ended up being really successful. And when NASCAR was going through all these developments, they were frequently providing updates to the teams, the OEMs, the drivers, and all that. But before they wanted to take it to the track, they came working with us to go through STAR-CCM to get basically as much confidence as they could get in this exhaust design before they built it and put it on track. And they did end up putting it on track at a Phoenix test, and they effectively saw all the things that we were seeing here in the models. They saw all these temperature reductions. So if we look at the inside of the cabin, uh, we can see a big temperature drop along that frame rail, the left side back near the driver, massive reduction in temperatures, uh, both sides of the frame rail front. And in the firewalls, we're seeing much lower temperatures as well. So their goal with this was run the simulations, find out all the changes they can make, and then hopefully see all those exact changes on the track. And running this through STAR-CCM really gave them the confidence to go through, build this, test it, and hopefully not have to show up to track with 10 or 15 different options to swap out. And they had the confidence to go through with this, and they ended up shifting all the cars to this design. One When they went to the track test, you do always want to come with a couple designs just in case. And although everything we were showing with the short exhaust was positive, uh, in case real world testing or manufacturing differences or anything like that was hiding something unexpected, they did show up with the option to cut out a vent hole inside the floor again, or supply extra cooling ducts, uh, which would pull some strong flow from the splitter or underwing and supply that back to the exhaust as well. In the end, the short exhaust basically gave them everything they were looking for. So all the modeling we did in STAR-CCM basically bore out once they took it to track and did some physical testing on it. The additional options that they had, while they worked and while they were useful, they went into the test knowing that those ones were the ones most likely to have, an impact on performance for the race car itself, whether it's more drag or less downforce, which they then saw at the track test. So they have these options in the future should there be, an exceptionally hot race day coming up for outdoor temperatures or anything like that, that they could help, reduce some of those temperatures as well. So in the end, they went only with the short exhaust, but came away with that design plus some other options for the future if they need them. And then with that, I'll pass this back to Monica and we'll answer any questions you have.
Thank you very much, Greg. And I wanted to start with figuring out who the NASCAR driver with the most votes is. And we had quite a few options in here. And I don't know if we have a slide with a name on it, but the winner of the poll from all of you is Denny Hamlin. So we'll have to wait a few more months to find out if we're all right, or if there's somebody else who kind of rises to the top. So there's already a few questions in the chat, so that's very good. You still definitely have time to put some additional quotes in or additional questions in. But one of the questions we had, Greg, had to do with speed, because if NASCAR runs at 175 miles per hour, why did you and or NASCAR pick 60 miles an hour for the test?
Good question. So for this case, it was focused on a street circuit, and typically when you're running on one of the high speed ovals or something like that, you have a lot of cooling flow and you have a lot of additional, convective cooling that you can use. with the street circuits and all the rapid acceleration and rapid deceleration, you end up with a whole lot of heat soak. And basically, the worst case scenario for needing the maximum amount of cooling while having the least amount of airflow to provide. So this was basically looking at the worst case scenario for where the issues for heating and cooling were needed, or heat removal was needed and cooling was needed. So if we can fix it there, we should be able to fix it at the higher speeds as well.
Okay, great. And then another question is how long do these models run for you how long do the results take to come back?
Yeah. So these, when I ran them, took roughly 24 to 30 hours to turn the model around. These were run in-house at the time on about 400 cores to give you an idea for turnaround time. This was a little over a year ago, and since then, more and more of what we were doing at the time has been moved off of CPU solving and onto GPU solving. So if I were to run this today, um, barring the radiation aspect of it, which I'm sure will come to GPU at some point, um, I would say that turnaround time would shorten from the 24 to 30 hours down to maybe 3 or 4 hours if we had a couple video cards to put at it.
Okay, thank you. Um, and in your this study, um, let me read it real quick. Did you have conduction, convection, or radiation?
We were doing all three: conduction, convection, and radiation. With temperatures up around 1,000 degrees, radiation becomes pretty important.
Okay, and then I have another question here. The cabin temps at 60 miles an hour was still 121 Fahrenheit, which is pretty toasty. Any ideas what the temperature delta is at nominal race speeds?
That's a good question. Since we didn't run this at the 175 mile an hour, oval race speeds, unfortunately, I don't have a good answer. I wish I did. But if I had to guess with, almost a tripling in speed, I would assume that we're probably going to drop another 20 degrees Fahrenheit roughly. And at that point, you also have a lot more airflow coming in through that window NACA and the left side window net venting into the cabin for a whole lot more heat transfer and cooling inside that cabin space.
Thank you. By the way, if there's still time to enter questions, we have a few more, but there's still time. Um, did you run this model on premise or remotely?
It was initially in house on 400 cores, like I said, but we also did run this outside the office on a local supercomputer for 400 cores as well when we were running more in tandem with NASCAR at that time. That said, if we were doing it now, we'd also have access to Siemens SimCenter Cloud HPC. So that would have given us another option, which would have mitigated, the need to push data here and there to submit the runs and do all that. Instead, we could have just basically launched it with one button click straight from the user interface, which would have been convenient.
Okay, so I have one question that's more related to STAR-CCM Plus. Do the capabilities come out in a yearly release? Like like a new release here?
They actually come out 3 times a year. So there's usually one out in February, July, and October, I think. Those are three fairly major releases. Plus, then they have the bug fixes about 2 months later, usually. So three large releases and three bug fixes each year for anything that pops up.
Okay. Any more questions from the participants today? Feel free to put them in now. Um, everyone who's on who's in attendance today is going to receive a recording of this webinar. And I really appreciate everyone participating today and for all your questions. And we hope you found it to be valuable. And thank you very much again, and have a great rest of your day.
Yep. Thanks everyone for coming, and thanks for the good questions.